All right, let's finish up the tail end of this lesson on integration by parts. Now, it's actually something that you saw a couple sections ago. It's kind of just a notation thing, but there's sometimes reasons why a problem is given this way. Remember, this is a differential equation. That's fancy talk for this is the derivative. What do you do with a differential equation? You solve it. But in calculus, that doesn't mean that you're solving it for x. It doesn't mean you're trying to find the solution in that way. It actually means that you're trying to solve it for y, which is actually like you're trying to find the original equation. So to solve a differential equation is to do the antiderivative and go back and find officially the y equals equation. All right, which means bottom line is we're going to have to use integration by parts. We still have to do the antiderivative. There's actually a whole class in college you can take. It's called Differential Equations. It's actually like a subsidiary of what we're doing in Chapter 6. Like it teaches you how to do all kinds of other antiderivatives. I'm just sharing that because there might be one or two of you that you go down a path that you have to take a class like that. I remember I took it, and then summer came, and then we went back to school in the fall, and there was an engineer that needed some help, and it was such a weird thing that happened. I could not remember a single thing. Do you ever have I could not remember. I couldn't even help this, and I was like, what is going on? I don't even know what I learned in that class, even though I worked so hard in it. So it was weird. Don't let that happen to you. Make sure you remember how to solve a differential equation. Okay? Now, if two functions are being multiplied together. Now, just stop there for a second. You guys are here. I'm actually trying to start to produce a big picture. If two functions are being multiplied together, do you realize that a week ago we were using the substitution method and two functions are being multiplied together? So how come we're not using the substitution method all of a sudden? Okay, that's a bigger question to be answered, but I just want you to be thinking that this problem has no inside whose derivative will cancel with the outside. Remember how we were so focused on choosing u? Well, that's because the derivative canceled. And if you're looking at this problem, you're saying, yeah, I don't even really see an inside or outside. That's why it's not going to be the substitution method. So what you're going to learn is if it's not the substitution method, then it's parts. But the good news is if it's parts, it's kind of fail-safe. You just use the Lipid test. And that's why, again, people kind of like this because you sort of don't have to think too much. Now, what do we got here? Do we have any L's? No. Do we have any I's? No. Give me a P. X. Okay, that's a power function. Sometimes it kind of sneaks or we don't recognize it, but it's the most simple power function. It's x to the first power. Now, you've seen this a lot today, but I just want to make sure that we're careful. If you go back to my lesson yesterday, not every u is a power function. It depends on what's given to you. Okay, but this one is, and that means dv is the rest of the problem. Now, I don't really have a dx unless I decide to slide this dx over here. It really doesn't matter. It's kind of a technical thing anyway. I don't need to write the letter dx right there. I am going to write a dx here. Otherwise, I wouldn't have anything to write down because the derivative of x is 1. I guess I could write the number 1, but I'll go ahead and write dx. Careful, I realize you're in class, maybe you're just taking notes, but you got to be thinking. You got to be thinking to yourself, what is the antiderivative of secant squared? When you came over to my desk back in November, you said the derivative of blank is secant squared. The derivative of blank is secant squared. So we want to go back to that function, tangent. Tangent. All right, I'm going to go ahead and just show you, because I want to write down what's really going on here. Instead of just putting an equal sign on the board, I'm going to put a y equals, because I'm now changing dy dx back to y equals. So it's uv, that's x, tangent x, uv, minus the integral of v du. That's, of course, tangent dx. I hope one of the things that you got from the video, or when you go watch the video, one of the things that you will get from the video is that you have to do the integral as part of the formula. Uh-oh, the integral of tangent? Wait, did we make a mistake? How do you do the integral of tangent? How do you do the integral of tangent? Now, at some point in probably the next 10 seconds, you're going to say that I already showed you this, but I still want to show it to you again, because the integral of tangent requires the substitution method. See, what I really want you to conclude is that to finish parts, I might need to substitute. Did you hear what I just said there? To finish parts, I might need to substitute. In other words, I can mix and match my methods. Yep, you can mix and match the methods. Because, of course, the big picture here is that we're just trying to find the antiderivative. Now, I'm going to still do it again, but again, some of you might be like, yeah, we kind of already did that. We did, but I'm still going to show the substitution method so you guys realize that it's not just kind of a magic show. Remember, we decided if you let the denominator equal u, then it'll cancel with the rest of the problem. It'll cancel with this sign. And so we basically do the substitution method, which gets us to a place where the signs cancel. Now I am skipping a step, but the signs cancel, pointing at these two signs. The cosine becomes the letter u. And you got to realize that this negative sign didn't cancel. It actually got introduced into the problem. Okay, the antiderivative of 1 over u, the antiderivative of 1 over u is ln. The antiderivative of 1 over u is ln, which kind of brings us back in our game of life right here. It's kind of like the game of life. Okay, I made $1 million. I'm getting ready to retire, and we're back to the answer. Or if you chose this route, in the game of life, you can kind of go one way or the other way. If I just chose this route, I just write down opposite ln of cosine. Now, seriously, you're not getting lost here in the game, are you? Do you guys understand the arrows? Okay, I'll say this too, this minus sign, like I said in the video, it sometimes becomes the only mistake that kids make. It disappears, it gets lost with this one. This one, of course, came from the antiderivative. But listen, when you're checking your work, and I do mean this nicely, when you're checking your work in the solution manual, if you see something wrong, like a plus sign, it should be a minus sign, I hope you don't just erase it and change it. I hope you go back and figure out why. A lot of times it has to do with stuff like sine and cosine. That answer from before lunch that I erased, same thing. If you would have one thing wrong, don't just change it. Try to figure out why, because that's the whole point of your assignment, obviously, is to learn so you can do it on a test or quiz. Is there anything I did right here that you have a question with? We started with parts, but to finish parts, to finish the integral, I had to use the substitution method. Fun stuff. Last problem. Okay, don't get dizzy, but this problem does seem a bit circular. Okay, it seems a bit circular. I hope you'll find out why. Okay, let's find out the antiderivative of e to the x cosine of x. Now, although I cued you in a little bit that there's something circular about this problem, okay, as with how most math works, you can still jump in, you should do what you would normally do. Okay, it's going to be the right thing. So we do the lipid test. Okay, give me an L, give me an I, give me a P, give me what's next? E. It's spelled lipid. E. Give me an E. E to the x. Okay, so we had to go the whole way down to the E to be able to choose U. That means that dV is the cosine dx. Do the derivative of e to the x. Hey, remember when I said you have to still know how to do derivatives from the first half of the year to do antiderivatives the second half of the year? We're right in the middle of it right now. Just in case you didn't notice, we're right in the middle. Your brain should be going in both directions. Remember, this is the antiderivative to go back to the v. I even had to double check, is it positive or negative sign? But it's positive sign. Okay, if you want to write down the formula, you're probably going to internalize this better. Okay, you should be writing down uv minus the integral of v du. uv minus the integral of v du. Are you guys all right with just the formula? We just plugged into the formula. Of course, has been said just about for every problem, you still need to integrate. So you should be asking yourself, how do I integrate e to the x sine of x? And yourself should answer you, parts. You have to do the parts method again. Okay, it's two parts, they're being multiplied together. It's not substitution. I don't have some type of cancellation connection. Back to the lipid test. Okay, remember what I showed in that first slide. There's something circular. We'll use that phrase. There's something circular about this problem. Are you anticipating? Are you wondering what that might be? Maybe you picked up on what I'm trying to do. That is kind of like show a box to represent like the next formula. Listen, kids, that's because of this minus sign. I'm telling you, this minus sign sometimes becomes the only problem in this answer. So this box I drew right here, I think I need it to be a little bigger, is going to represent my next parts, my next UV. That's negative e to the x cosine of x minus the integral of v du. I put the negative sign in front. Now minus the integral of v du. I want you to be able to check your work, especially if you're not just copying, but make sure you're keeping track of things, because we're going to have a real negative sign party here in a second. Okay, ready? First of all, we've got two negatives inside here, those two negatives. Second of all, we have this minus sign, which is technically in front of this whole answer, or this whole box. That minus sign is going to distribute. I'm going to distribute it right now. It's going to change that sign. It's actually going to change this one, if you will, back. But that negative sign just got distributed. All right. I'm staring at the integral of e to the x cosine of x. And I'm going to add something to the end of that little sentence. I'm staring at the integral of e to the x cosine of x. Again. Again. When was the first time you looked at it? Wait a minute. So how do I do the integral of e to the x cosine of x? Well, you have to do this. And then guess what's going to happen? I'm going to get to the integral of e to the x cosine, and then how do I do the integral? Maybe I should change this problem to be that it's a little more like Groundhog Day. If you're into movies and stuff, I feel like I'm in Groundhog Day. I keep seeing the integral of e to the x cosine of x. You kind of wake up. I've been here before. All right. We're going to get out of the cycle. Okay. We're going to get out of the movie. And here's how. It's pretty cool. It's by understanding this equal sign right here. It's funny, we use equal signs a lot in math, but guess what it's equal to? It's equal to what I started with. You know, based on the idea of what I'm trying to do, this thing I started with is supposed to be equal to this thing that I'm creating. So let's use the equal sign like we've never done before. Let's actually say that these are equal. And now what I want you to do is feel like you're a little more in an algebra class. What do you do in algebra classes? Usually solve equations. Guess what I'm trying to solve my equation for? I'm trying to solve my equation for the integral of e to the x cosine of x. Are you tracking with me? Okay. Now, I've got one over here. They're like terms. I'm going to add this integral of e to the x cosine of x. I'm going to add it to the other side, because if that's what I'm trying to solve the equation for, I better collect those terms. Now how many integrals of e to the x cosine of x do I have? 2 integrals of e to the x cosine of x is going to equal e to the x sine of x plus e to the x cosine of x. By the way, we just kind of got out of the movie, we got out of the cycle, but we still have one more algebra step. Okay, we're trying to solve for the integral of e to the x cosine of x. Just get this 2 out of here. Of course, divide it. So 1 integral, I'm going to erase these 2's, 1 integral of e to the x cosine of x is equal to half half of e to the x sine of x plus e to the x cosine of x. Plus c. Plus c. I don't want to ruin all the fun, but I do want you to understand calculus. Eventually, you should get to a point where you're like, how do I know if this is going to happen? Or could this happen for another problem? Think about the two functions that you were integrating. They basically have the ability to go back to where you started, right? Eventually, the cosine is going to bounce back to a sine, or bounce back to a cosine. My fault. It's going to bounce back to a cosine. E to the x doesn't really bounce at all. It just stays the same. So is this the only kind of function? I'll say that it's the only type. It's got to have an e to the x. It's got to have a sine or cosine. Because as we said, those two functions have the ability to bounce back. In other words, as I go through these steps, to kind of get back to the exact same starting point. Once you get back to that starting point, stop the cycle. Wake up from the dream and do my little equals trick. All right, well, that was a conversation stopper. That's a neat problem. And you have a whole assignment full of these kinds of neat problems.